Hey Kipsters, we're almost at the end of Module 4. We're working on Lesson 27, the nature of solutions of a system of linear equations. If you're thinking back to some earlier lessons, we were talking about solutions and the different types of solutions that we could get. And we said that when we got down to one particular number that x had one solution. And when my left side equaled my right side, that there were infinitely many solutions. And then in particular, when my left side didn't equal my right side, that there were no solutions at all. What we're going to do in this lesson is identify the slope of two linear equations and compare them. And then we're going to identify the y-intercepts of both those equations and compare them. Then we're going to use our observations, our comparisons, to form conclusions about the graphs of the equations and their solution set. So let's take a look at number one. I'm going to zoom in on number one. So we've been asked to determine the nature of the solution to each system of linear equations. Well, I know that I can be given equations in several different forms. Particularly, I've been given an equation, one in standard form and one in slope-intercept form. It's easier for me to identify my slope and y-intercept when an equation is in slope-intercept form. So what do I do when I've been given an equation in standard form? I isolate for y. I'm going to model doing that in number one. Particularly equation 1, 3x plus 4y equals 5 is in standard form, and I want this to be in slope-intercept form. So I know from previous videos, I start by moving my x term away. I'm going to use the subtraction property of equality to move my x term from my left side to my right side. On my left side, 3x minus 3x will cancel out, and I'm left with 4y equals 5 minus 3x. I'm closer to getting my y alone, but I'm not there. What do I need to do to isolate the y? I need to use the division property of equality. Notice on the right side, each term is divided by 4. So 4 divided by 4 cancels out on the left. I'm left with just my y. 5 over 4 is an improper fraction. And I have a negative 3 over 4x. So this looks like slope-intercept form, except I probably just need to rearrange my equation so that my x term is in the front. So we're just going to go one line below and do that. So y is equal to a negative 3 over 4x plus 5 over 4. I'm going to box that out. So our whole goal is to compare systems of linear equations. So I'm going to rewrite this. To compare this system of linear equations, I am comparing y equals negative 3 over 4x plus 5 over 4 to y equals negative 3 over 4x plus 1. What do you notice about the slopes of these lines? You should notice that the slopes are the same. Slope is the coefficient attached to the variable x. So if I see a negative 3 over 4 by both of them, I know that my slopes are the same. Well, first off, let's just stay on slope. When I notice that my slopes are the same, what does that tell us about a line? Think about lesson 26. When our slopes were the same, did that create, what type of line did that create? Yeah, the slopes are the same, so I know the lines are parallel. All right. So a key vocabulary word has come out, parallel. What do we know about parallel lines? We know parallel lines run in the same direction and they never touch. So that means if these lines have the same slope and they produce parallel lines, there is no solution. There is no solution to this system of linear equations. Let's go ahead to example number 2. Example number 2, I've been asked to do the same thing. I want to determine the nature of the solution of each system of linear equations. Both of my equations are in what form? Both of my equations are in standard form. I want both of them in y-intercept form to be able to compare them. So let's pull out the first equation. And I want to move my x term from the left to the right. Begin to isolate my y term. Y is not alone, so I want to use the division property of equality. I'm going to divide each term by whatever is attached to y. 2 divided by 2 cancels out, and I'm left with y equals negative 4 divided by 2, negative 2, and negative 7 over 2x. One step away from this being in slope-intercept form, I'm going to rewrite this to where my x term is in the front. Box that out. All right, now I'm coming over to x minus y equals 5. What term am I going to move? So normally we would move our x term, but remember our goal is to have our y term positive. So let's play around with it. Let's move our y term first from the left to the right. Notice my y was being subtracted on the left, so I added it to move it from the left to the right. Y's are going to cancel out on the left. Now x is equal to 5 plus y. I want the y alone, so I'm going to subtract 5 from both sides. 5's are going to cancel out. Now I'm left with y equals x minus 5. Well, I'm going to go ahead and stack these equations, the system. So I'm comparing y equals a negative 7 over 2x minus 2. So y equals x minus 5. What do you notice about our slopes? Yeah, I noticed that the slopes are different. Particularly in equation 1, my slope is a negative 7 over 2. And in equation 2, my slope is a positive 1 over 1. Because my slopes are different, okay, that's going to mean that these two equations are not two non-parallel, are not two parallel lines, they're actually non-parallel lines, and at some point they will intersect. So that means this system has one solution. Let's take a look at number 3. Both of my equations are in standard form. I want them both in slope-intercept form. And I'm going to pull out 9x plus 6y equals 3. And my goal is to isolate the y variable. Go ahead and do that work. Okay. I'm going page number 2. All right, so I have converted both of my equations into slope-intercept form. So I'm going to rewrite them like I've done on my problems where I'm stacking them back as a system of linear equations. What do you notice about your slope? I notice that my slopes are the same. What do you notice about your y-intercepts? I notice that my y-intercepts are the same. When our slopes are the same and our y-intercepts are the same, this line will have infinitely many solutions because both lines are in fact the same line. So this line, or this system, this system has many solutions. To recap my thoughts around the nature of solutions. So there are 3 types of solutions to a system of linear equations. If I see the same slope but a different y-intercept, there's absolutely no solution to this line, particularly because same lines with the same slope are parallel. And we know parallel lines run in the same direction and never touch. If I see different slopes, okay, I know that these are not parallel lines, so they're 2 distinct lines that will cross at one point, so there's one solution to that line. And I know if I see the same slope and the same y-intercept, that is the exact same line, even though the equations look different, and that there are infinitely, I'll add this to it, infinitely many solutions. Take a second to get that down. Let's keep pushing. let's look at this system of linear equations. Based off of the work that we've just done, determine the nature of this system of linear equations. Yeah, you should have been able to evaluate our slopes and see that because our slopes are different, that this system of linear equations is actually going to have one solution. That means those lines are going to cross in one place. So I'm going to plot my first known points, 0 and 5 and 0 and 3 from both lines. And then I use my slope from each of them to move, and I generate this graph. And so I generate this graph of the linear system of equations. What do you notice about the solution set? I'll zoom in on it because it is kind of tiny. What do you notice about the solution set? Hopefully you picked the answer choice that said you noticed that my answer wasn't going to be a whole number. When it's difficult to identify the precise coordinates of a solution, we can solve for a system of linear equations algebraically. Let's go ahead and solve for this particular system of linear equations algebraically. Let's take a look at my system of linear equations. I notice that both of them are in terms of y. What this allows me to do is to actually eliminate the variable y and set both sides of the expression equal to each other. Okay, so because these are both set equal to y, I'm actually saying that these are the same thing because y equals y. All right, so now that I've eliminated the variable y, my goal is to solve for x. So I'm going to move 3x from the left to the right side of the equation. I'm left with 5 on the left equals 5x plus 3 on the right. I haven't done my job to isolate my x, so I'm going to subtract 3 from both sides. Now I get that 5x is equal to 5 minus 3, which is 2. Last step, I'm going to use the division property of equality to divide both sides by 5, and I get that x is equal to 2 over 5. Once I've solved for x, I'm going to use x. You're going to use x in one of your systems of linear equations. You can use x in any one of them, but I'm going to particularly use x in equation number 1. So I'm going to write it. When I'm multiplying a whole number by a fraction, I can make my whole number a fraction by putting a 1 under it, and then I'm going to multiply straight across, so y is equal to 3 times 2, which is 6, over 1 times 5, which is 5. So I have 6 over 5 plus 5. I actually end up with the y coordinate of 31 over 5. Well, what do you do with an x and a y? You put them together as in ordered pair. So I am saying that the solution to this system of linear equations is saying that the solution to this equation is an x of 2 over 5 and a y of 31 over 5. Let's compare that to our graph. My y is 31 over 5. How many 5s could go into 31? About 6 and some change. What's the y value? Compare our y value to my y coordinate on the graph. Does it look like my y value at this point would be 6 and some change? Definitely. Example number 4. So we're being asked to determine the nature of each system of linear equations. If the equation has a solution, we're going to find it algebraically and then verify that our solution is correct by graphing. So let's look at number 4. Both of my equations are in standard form and I want them in slope-intercept form. Let's make that happen. So now that I have 2 equations in slope-intercept form, I'm going to stack them again as a system to compare them. I'm comparing y equals negative 1x minus 7 to y equals a negative x minus 7. I know that there is an understood 1 in that second equation. So what does this tell me about my lines? What do you notice about our slopes? What do you notice about our y-intercepts? You should notice that the slopes are the same and y-intercepts are the same, therefore this system will have infinitely many solutions. All right, let's look at number 5. So number 5, I have one of my equations already in slope-intercept form, but my second equation is not. What does equation 2 look like in slope-intercept form? All right, so let's take a look at number 5. I'm noticing for my system of equations in number 5, it doesn't look like anything I've seen before. So this is a great opportunity for me to introduce a new skill. When I examine both of my equations, I see that I have y terms on my left, that I have an x term on my right, and a constant on my right. I could do something mathematically to be able to set my expressions equal to each other. So I want you to think back to the example that we worked where both of my terms were equal to y. When both of my terms were set equal to y, I was actually able to set the expressions equal to each other and isolate for the variable x and then use x to solve for y. I can do something similar here. What's missing from my first equation on the left side that's in my second equation on the left side? You should notice a 3 is missing. What I can do is pull out the first equation, and I'm actually going to multiply my left side by 3 and my right side by 3. So I put the entire equation in parentheses, and I'm multiplying it by 3. That means each term is going to be increase times 3. So my new system of equations that I'm evaluating is 3y equals 9 over 2x minus 3, and 3y equals x plus 2. So I know, because these are both in terms of 3y, I can in fact set them equal to one another. And solve for x. Then use my x to solve for y. All right, so I'm working with an improper fraction, and I want to get this fraction out of my equation. What do I multiply by to eliminate a fraction from an equation? Yep, I'm going to multiply by my denominator. But remember, whatever I do to my left side, I must do to my right side. So I'm going to multiply on the left by 2. Notice the 2 is going to cancel out. I'm left with 9x. But this 2 has to also be multiplied by that negative 3. So it's 9x minus 6. And on my left side, this 2 is going to be multiplied by x to be 2x plus 4. All right, I want to move 2x from the right over 7. Well, I want to use x to solve for y. How do I use x to solve for y? I'm going to substitute x back into one of the equations. So I'm just going to choose the first. We have the factor of 2 in common, so I'll simplify this fraction to be 15 over 7 minus 1. When you compute and do that math, you're actually doing 15 over 7 minus 7 over 7. Which leaves us with y equaling 8 over 7. What's the solution to this system of linear equations? The solution to this system of linear equations is 10 over 7 and 8 over 7.